Thank you very much for the organizer to organize this meeting and to give me this opportunity. So it's a joint work with David Chiron and Thierry Goudon from Nice, like me, and also in a transatlantic collaboration with Nader Masmoudi in New York. And so all this work started by contacts with experimentalists, so I want to thank them too. So this is the group around Robin Kaiser in Nice, William Guérin, Robin Kaiser, and Guillaume Labéry. And these are the people able to run this kind of experiment there, about which I will talk to you a little bit. So I'm very grateful to them to talk with me about what they're doing. And also Alain Olivetti, who performed some simulations I will show you later on. So here's a biggest picture of this experiment. So there is no scale. Sorry about this, but it's a well, tabletop experiment, but a big table maybe, but still it's not extremely large. So to give you an idea of the scale, so the important thing here will be the small. Do you see it well? The small cloud here, more or less reddish. So this is a cloud of cold atoms, rubidium in this case, and it's about, say, 1 centimeter or maybe at most a few centimeters wide. And so there is a vacuum chamber here, and you can guess there are many lasers that are hitting the cloud. And you can maybe also see here, this is a coil where electric current is flowing, and it creates a magnetic field inside. So we'll just give you a few ideas about how this works. This is called the Magneto Optical Trap, because the atoms here, they are trapped by the lasers and by the combined effect of the lasers and the magnetic field, which is here. So we'll start, as you have understood, we'll start by a little bit of physics. So here's the basic principle. So it's the scheme is really much simpler than the previous experiment. So it's a very simplified version of all what's going on in the experiment. So the first remark is that, well, I can use a classical description of the atoms, and we've heard yesterday about how complicated can be the quantum kinetic equations. So I'm grateful that actually the atoms, albeit cold, they're not so cold that quantum description is needed. So they will be considered as particles, and the kinetic equations I will use are classical. So then, how does it work? How come that these atoms they keep trapped in the picture that I've just shown you? So first, they're say trapped in velocity space. That means they're just slowed down by the process. So what happens? So this is just one atoms, and these are two lasers. Actually, there are more than two, but here is just two lasers. And the basic principle is a Doppler effect. So imagine the atoms is traveling towards the left, and the atom sees photons from these lasers and from this one. And since it's traveling in this direction, it sees these photons with a slightly higher frequency than these ones. And because of this slight difference in frequency, this atom will absorb more photon coming from here than coming from here. So each time you absorb a photon, then you feel a kick that corresponds to the momentum of the photon. So if you absorb more photon coming from the left and from the right, then the net force is going to the right, opposite to your velocity. That's a friction, if you like. So that's a very simplified version of what's called Doppler cooling. But essentially, that's the idea. So this gives you a friction for the atoms. Now, what happens for trapping in space? How come that they don't just go away? Because then there is also the magnetic field, and actually magnetic field gradient, and it's a mechanism similar to this one that transforms this magnetic field gradient into an effective trapping force. So there is also an external force acting on the atoms. And so that's not all, because what happens, so you imagine you have your atoms in your cloud and they're shined by the lasers, so they absorb a lot of photons, and then what happens when an atom absorbs a photon, then they will re-emit the photon in a random way, in a random direction. So if I'm the atom and I re-emit the photon in this direction, then I feel a kick in the opposite direction. So if I say average this process over a sufficient number of cycles of absorption and re-emission, I can model this by a kind of Brownian motion velocity space. This is what I call here velocity diffusion. So these are the three basic effects happening in this trap. So there is a linear friction. If there is only the linear friction, then the atoms would just cool down to 0 temperature. But there is this velocity diffusion due to the random emission of photons, and also this external trapping potential. So far, this is just a one atom effect. There's no interaction between the atoms. But actually, there is. And this is the basic principle of the interaction inside the atomic cloud. So again, so now there are several atoms in the cloud, and these atoms here, and I absorb photons coming from the lasers. So I absorb one photon, then I re-emit it in a random direction. So now consider, for instance, this one. Then there is a probability that this atom here will absorb a photon emitted by this first atom here. And if it absorbs this, then it feels a kick in the opposite direction. So again, if you average this process about after a lot of cycles of absorption emission of these atoms, so these cycles of absorption emission are quite quick, then there is an effective force. This atom feels an effective force in the opposite, so in this direction, opposite here. So it's a repulsive force. And if you think of it a little bit, then it should be proportional to the surface here of the sphere around these atoms. So it's proportional to 1 over r squared. Repulsive force proportional to 1 over r squared. Then it's like a Coulomb force. So this is the atoms, the force filled by, for instance, this atom I due to all the other atoms. And you see it's just a sum of Coulomb forces. Of course, it's not real Coulomb forces. The atoms are neutral. It's just an effective force that is due to kind of exchange of photons. So this exchange of photons, this is the quantum process, but then I will forget about the photons and replace just the photons by all the forces I've been talking about, and by the Coulomb force here. So it's of course between the quantum processes and the approximation by a Coulomb force, there are a lot of approximations involved. So it's a very simplified version of what's going on in the trap, but still more or less it's considered a standard model. It was introduced, say, in 1990 by this physicist. You might know Carl Weyman. He went on to win the Nobel Prize then for the Bose-Einstein condensate. So now let's put real equations behind these models. So what do we have? So I have this effective two-body Coulomb force. I recall you, it's not a Coulomb force, but it's an effective force that looks like a Coulomb force. There's the harmonic trap, linear friction, and velocity diffusion. And so it looks like it's a trapped plasma. I have the features of a plasma here in a trap, plus dissipation and diffusion in velocity space. But there is, of course, the analogy with the plasma stopped before you have to introduce magnetic fields, because here I have no equivalent, so analog of a magnetic field. There is indeed a magnetic field, but it has no effect, no direct effect on the atoms. So the equation is this one. So the basic equation would be Vlasov-Poisson and then Fokker-Planck for the dissipative and then diffusive effects. So you can recognize what's going on here. This is the external potential. This is the self-consistent Poisson potential. So this is the equation for the self-consistent Poisson potential. And this is the Fokker-Planck operator. So in velocity. So it's already in a high-dimensionalized form. And what's important, so I've put it here, the Fokker-Planck operator in red, because sometimes I will keep it, sometimes I will remove it, but it will not change a lot in the main results of this talk. So. Yeah, it's the density of the atoms. Yeah. No, well, but rho epsilon is just the density. Well, f epsilon is density in a velocity n space, and rho epsilon is the charge, is the density of atoms. Rho epsilon is the density of atoms. But it's not. It's an effective. It's an no. It's an effective Poisson equation, right? Look, this is the force you have, and here in front of this, you don't have really the charge. It's not the charge here because the atoms are neutral, but because it's not a Coulomb interaction, but the atoms, they're exchanging photons, and these photons you can model this exchange of. Yeah, sure. Why does it have the Coulomb form? No, it's quite easy to understand. What's the probability that these atoms here absorb one photons coming from here? Well, you see this, if you think in terms of probability, I'm the atom and I emit in a random fashion my photon, then the effective section will be proportional to the surface of a sphere around me, and the sphere around me, that's 1 over r squared. So this is where the 1 over r squared come from. Yeah, then I'm coming to here. I'm coming to this. Yeah, it's an effective one. And well, anyway, this comes from the I-dimensionalization, but why did I choose this one? Of course, epsilon will be meant to be small. And what happens is that, so in their experiments, they can pretty much control how many atoms they put in the trap. And the more atom you put, of course, the stronger this kind of force become. So there is essentially proportional to n. There is a sum. So here, it can become strong when they increase the number of atoms. So they can, increasing the number of atoms, they go from a regime where the pseudo Coulomb force is small to a regime where it's large. And I'll be interested in the regime where it's large. So here I have already put this 1 over epsilon here. That means that I will be in a strong interaction regime. Sorry? The grad, where does it come from? It's here. It's an effectively. Yeah. Grad B creates an external potential, which is more or less harmonic, but well, more or less. And if you want full modeling of this, then all terms get mixed. It's horrible. That's kind of the simplest model. So still a little bit of physics. So these are the orders of magnitude that are involved. So they're using rubidium atoms. And so this is a number of atoms from 10 to the 6, say, to 10 to the 10, more or less. Of course, they can do even less, but then maybe they don't see many things. So they can control this quite well. So the cloud size is this range, say, to centimeter range at most, which is actually quite large. So there are many Magneto Optical Traps everywhere in the world, but these ones that in this they're quite large and stable. And temperature is millikelvin, so which is of course not very hot, but it's way above what would be a Bose-Einstein condensation temperature. Okay, so then just a few test numerical simulations. So first, I'm a little bit embarrassed because we've seen several very nice numerical simulations, and here I will present you some, well, I would say test numerical simulations. So they're really not very precise and not as maybe well controlled as the one we've seen 2 days ago. So the thing I want to tell you, so you see, if you have 10 to the 6 atoms, then you are to the point, it's not like if you have 10 to the 20 electrons in a plasma, so you're to the point where you can think of simulating one numerical particle per one atom, right? 10 to the 10, it's maybe not quite, but not so far from being possible if you put a lot of numerical efforts. So, so we decided to go for a discrete model, and we really simulate here so particles. You have particles, and you will see the particles. Of course, the density of particles is supposed to be approximated by the Fokker-Planck equation, the Vlasov-Poisson-Fokker-Planck equation I've just shown you. So, some words on the numerical simulation. So, in these simulations, there are only 8,000 particles. So. So they've been performed by Alain Olivetti, so he could do more, but these are just test simulations. but they're not so easy just because of this Coulomb force. So of course, Coulomb force on each time, everyone interacts with everyone. So on each time step, it's costly to do the computation. So actually, he's using what is called a tree code, which is a trick that was invented, I guess, for simulating large self-gravitating system. And he's adapting this thing for these simulations. So this speeds up a lot the computation of the force at the expense of a small approximation. So there is the friction and noise in this in the simulation you will show, and the external potential is assumed isotropic and quadratic. So in the experiments, usually they assume it's quadratic, but it's not really isotropic because of this magnetic field gradient, which is not the same in all directions. And then, since there is a friction and a noise, at some point all atoms would essentially stop. Except for the noise, so then an external force is added so that you still see some motion. So I was not able to embed my video in this, so I hope that's trying to work. Okay, so let's say this. Okay, so these are the particles there. So it's a 2D. They're in 2D simulations. Otherwise, we don't see much. And this is just a histogram of the density. So you see, the density is pretty much constant in a ball, so in a disk here. And now there's an external force that's pushing somehow, so you can see a rotating motion. And so what's important to notice is that really there seems to be a limit density that is very well defined, which is one, say, constant density inside and zero outside the ball. And of course, then you have some flow here that should be incompressible, right? Otherwise, you would have fluctuations in the density, and it goes on. So I will stop here. So now, from now on, then our goal will be to obtain then a fluid description for this dynamics, because then that will be easier to analyze and to implement numerical simulations and so on than for the full Vlasov-Poisson-Fokker-Planck equation. So now we're a bit coming to the mathematics. So the first notable thing is that there is a well-defined limit density. So if you take your equations at leading order and you minimize the energy at leading order, then you've got what should be the limit density, and it should solve this variational problem. So this is the external field here. So this is the external energy, if you want, trapping energy, and this is the self-consistent Poisson energy. So if you remember here, these are the leading order. So this one, there's one over epsilon here, one over epsilon here. So at leading order, they essentially balance. So here's the variational problem you have to solve. And so it is a very classical one, very well understood since, I think, the 20s at least, or even less, because it's called Gauss variational problem. So maybe Gauss already worked on it, I don't know. But it's not so easy. So here's what happens in a very simple 1D situation. So here's that's the trapping potential, and I put this and this is the solution. This is the minimizer for this problem here, the limit density. And you see it has compact support, and it's actually constant on its support. And that's a typical case. So if you take a more complicated potential here, and well, and more dimension, it will be a bit more complicated, but that's typical. The minimizer will have compact support. We'll call big K the support, and on the support, the minimizer is equal to Laplacian of the external potential. So it's quite easy to see. And of course, if I have a quadratic potential, then Laplacian is constant. So I have this. But still, it's not so easy because this K, well, in 1D it's easy, it's a segment, but otherwise it's a free boundary problem, and finding what K is really is not a trivial problem. And for the mathematics we need to do later on, we need some regularity on this boundary, and that's not so easy to ensure that really the boundary of the support of the limit density is as smooth as we would like. And well, this is a small side remark that could be useful, is that actually you can transform this problem in an obstacle problem, which is a classical free boundary problem for elliptic PDEs, and that could be useful. So some example. So the first example you've seen is the numerical simulation. If you have quadratic potential and isotropic, then you have a constant density and the support is just a ball. Then if you have something which is quadratic but not isotropic, then Laplacian of quadratic means constant, so you still have a constant density, but then the support is not a ball anymore, it's an ellipsoid, and you have some explicit computation. But here this is the situation. So in blue, this is the external potential. So these are level sets of the external potential. They're ellipsoids. But and you see here the support of the density. So it's also an ellipsoid, but not the same as the external potential. And you can see it's much thinner. So if you have if the potential is elongated in one direction, actually the limit density is even much more elongated in this same direction. So this is an interesting effect. And now, if you have more general potential, then the limit density is not constant. Well, if you assume that the potential is radials, and then it's still a ball, but not constant in this ball. So these are some examples, but it can be as complicated as you like, essentially. So now we have the limit density turned to the say a dynamical problem. I have the limit density. I want to understand the dynamics and the velocities of my particles. So actually, the same problem. So if you go back to my basic equation here, you remove the Fokker-Planck operator here, you remove the external potential here, and you put it on a say torus, and you put a neutralizing field here, neutralizing background here. Then you have a problem that has been well studied. For instance, by Julien Barré and Masmoudi, at least also Emmanuel Grenier beforehand. So it's called quasi-neutral because in this case the density of in this case they were thinking really of electrons. So density of particles is close to 1 or to some fixed number. So it's quasi-neutral. And so in 2000, Julien Barré proved that if you start with well-prepared initial data, and I will go back later on what does that mean to be well-prepared. So one thing is that it should be close to some monokinetic velocity distribution. Then this, if the initial data is close to this, then it remains close to this in time, and the velocity to which the f is close to solves an incompressible Euler equation. And then these results were really refined by Nader Masmoudi 1 year later, because he showed that he actually, if you allow some fast oscillation around the limit velocity, then you can deal with not so well prepared initial data. I will come back to this also a little bit later. And then recently, Maxime Auret and Daniel Anquan, they've studied this limit process, but instead of Euler, towards a limit kinetic equation. So it's kind of a generalization again of this in some cases. So here, what are the different features that we have to deal with respect to these previous works? So we have a finite charge. So have you seen? So the limit density is not constant. Or it's just constant on its support. But then there is the problem of the boundary. So we have to deal with non-constant limit density and with the boundary conditions. And also potentially, if we want to add it, and that's you have to add it if you really want to model the experiments I was talking about before. Then you have to add a Fokker-Planck operator. So now here is the theorem. So first hypothesis. So we need well-prepared initial conditions, and in the sense of Julien Barré, so the ones which are strongly well-prepared. And what does this mean? So this is the total potential energy. So this is the self-consistent potential energy with the pseudo-Coulombian energy. This is the external potential. So this is the leading order, and these are fluctuations. So we want actually also that the fluctuations are small. These ones, we want all this to be small. So it means that really we want to start close to the limit density. And we want to be close to a monokinetic distribution of the initial distribution. So V0 will be our initial velocity distribution, and we want to be close to this. And so this is the velocity dispersion around V0. It has to be small. And also we want that this initial velocity V0 is divergence free and satisfies a no flux boundary condition. The domain, of course, will be the domain where the limit density is non-zero. So you can see this is strongly well prepared in this sense, initial conditions. And now, what's then the statement of the theorem? The statement of the theorem is what we could hope for, is that in the sense that, so this is the incompressible Euler equation that you probably can recognize here. So incompressibility equation here. This is the boundary condition, no flux boundary condition on the, so in this case, I'm stating it in the harmonic and isotropic case. So it's my domain is just a sphere or a ball, and the boundary of the domain is a sphere. So I have a no flux boundary condition. So the density here, it converges to a limit density rho star, which is the minimizer I've shown you before. And if you look now at the current here, well, essentially it will be a limit density times a velocity, and this velocity v solves indeed the incompressible Euler equation. So we have the convergence we were looking for. So if we are really in this strong interaction regime, and if with strongly well prepared initial data, then we have the hope that we can simplify our description of the dynamics in the trap using just the incompressible Euler equation. So we have already had examples of this before. This limit is singular in the sense that, of course, beforehand we had Vlasov equation plus Poisson equation, or Poisson-like equation, and now Poisson equation, in a sense, has just turned into this incompressibility condition there. So before I tell you a few words about the proof, what can we tell? So here's the density in the case of harmonic and radial, so the simplest case, but actually generalizations are not so difficult. So the first generalization is if you want to state it in a ellipsoid, for instance, and then there's no problem because then we know that the support is the ellipsoid and it's as regular as we would like. So there's actually no difference except that you have to replace this by the right support. Now, in the general case, it's a bit more subtle because then the domain, you don't know a priori what the domain K is, and you have to find it by solving your rational problem, which is okay, but we will need some regularity of this domain, and it happens that some cusp may, it's hard to exclude the possibility that the boundary of the domain has some cusps. So we have to exclude this, otherwise we don't have enough regularity. So let's assume that we have been able to exclude the case of cusps, and we have now general potentials. Now, rho star, I remind you, this is the Laplacian. On its support is the Laplacian of the external potential. If Laplacian of the external potential is not constant, then rho star is not constant. So, well, it's not incompressible anymore, really, and your divergence free velocity becomes this equation there. So rho star does not depend on time, really. It's fixed by my variational problem. It just depends on space, and V depends on times and space, and has to satisfy this constraint here instead of the incompressibility conditions. So actually, I didn't know. So Euler equation is just modified by this by replacing incompressibility by this. Beforehand, I didn't know these equations had a name, and now I've learned that when you replace incompressibility by this is called the lake equations, because probably it has been used or introduced to study hydrodynamics in lakes. And then, okay, one more generalization is adding a Fokker-Planck operator. If you choose the right scaling, and I will turn to that later on, then what happens is that not much changes in the proof, and the Euler equation here you have to add this red term here, which is just friction, right? So the friction survives in the limit. Not diffusion, because you will see that the scaling is such that this disappear. Just here, see that there is this. You have to assume that this goes to 0. It will be in the scaling that both epsilon and theta goes to 0. So, okay, a few words about the proof. Third thing, so you have a solution to the limit equation. Of course, it's defined on the domain, so you have to extend it on the whole space. So this strange V will be the extension of this to the whole space. And this is the expansion of the potential energy that I've shown you before. And the key quantity, which was already introduced by Julien Barré, is this modulated energy here. So you can understand, so it tells you how far you are from limit density rho star and how far you are from monokinetic distribution. So if this is small, it means that you are close to a monokinetic distribution with this velocity. And if this is small, it means that your total potential energy is small. It means that your density rho epsilon is close to your limit density rho star. So really controlling this modulated energy, or sometimes called relative entropy, will be the key. So what does it mean, well-prepared initial condition? Actually, well-prepared initial condition just mean that this is small, right? If you remember what it means to be well-prepared, it means that this potential energy, initial potential energy was small, and then this also was small. So well-prepared means initially the modulated energy is small. And then the key computation is just to derive this modulated energy and to use then the dynamical equation and to use the Euler equation and so on, and to use also the boundary condition in clever ways to show that if it is small initially, then it will remain small for up to some fixed time t. And for this, we need this other ingredient, is that with respect to the previous computation, then we have to deal with the boundary. And this is where some problems happens, and this is where we need some bounds on this potential here, on this external potential here. So we have to understand how the external potential behave close to the boundary. Okay, so this is where we need, for instance, some regularity on the boundary and so on. So we also have to deal, if we sometimes with a Fokker-Planck operator, if we want to have it. So in this case, the modulated energy has to be a bit modified. So we call it modulated energy Fokker-Planck. It is the same as before, and which may not come as a surprise. You have to add this kind of entropic term here with a theta inside, and this is just to ensure positivity. And then in the Fokker-Planck case, as I told before to answer a question, we deal with the small epsilon and small theta regime, which is, say, not absurd experimentally speaking. So this is why we chose it. And of course, since it was possible to make a theorem of it, it was all the much better. So I'm almost done. So what's the consequences of this? So of course, now we have, at least in some experimentally reasonable regime, we have simpler model to analyze well, numerically and also qualitatively. What physicists are looking for, they are looking for some models where they have really a few parameters and they can classify different regimes they have to deal with. So if they have something like incompressible Euler equation, then it is relatively easy to understand what's the different kind of physics that can happen. And for instance, in the physics literature, usually if they want to use fluid equation for this, they use Euler-Poisson equations. So and then they say it's strong interaction with Euler-Poisson. Well, if you have Euler-Poisson, then maybe it's as good to use this incompressible Euler, right? Another thing is, if you remember this picture of the very elongated domain in an anisotropic trap. So this is something that they may be able to control in the experiments. Their external potential, they have some ways to control it. So maybe this there could be some experimental test on this shape of the limiting density. This is probably not too difficult experimentally. And then, well, mathematically and also physically speaking, this is something we're not very satisfied about, is that we have a result, say, in the spirit of Julien Barré, which means that we deal with very well-prepared initial conditions, and maybe we would like to deal with less well-prepared initial conditions, right? And for this, we have tried to follow the road that was paved by Nader Masmoudi. But then, and to understand this means we have to understand the oscillations created by the electric field, well, pseudo-electric field, sorry. But then the interplay with the boundary layer close to the boundary of my domain is complicated, and we don't know how to do that for now. So I stop here. Thank you very much.
Yeah, it's when you take in your limit, the temperature goes to 0. I'm wrong?
Yeah.
And if you don't scale in a different way, in such a way that the diffusion has a macroscopic effect, what is the equation you?
A macroscopic effect?
I mean, if the diffusion disappear in the limit, right?
Here, you mean if
here,
the diffusion,
in the incompressible case.
Well,
otherwise, what do you expect to be true?
It will be a problem, because if it does not disappear, then you will be far from the monokinetic case,
yes.
Right? So one thing that might happen is that actually you might follow the idea of Maxime. Instead of going to fluid equation in the limit, like Euler
no
equation.
hydrodynamics, kinetic picture.
Yeah, then you have to keep a kinetic picture. Still, you could have something that you could reduce a little bit the equation using the fact that the interaction is strong, but still you have to stay in the kinetic framework. That's my guess.
I didn't completely catch this boundary. Where is the boundary? All this discussion. It is the exterior boundary of where rho is non-zero, or other type of boundary?
No, the boundary. Yeah, boundary is here, for instance. So this is the where the limit density is non-zero is in red.
Yes.
And outside is, and you have to understand what happens. So this is the limit density. So your real density f epsilon, of course, is close to this, but it's not zero.
So making the assumption that the boundary is smooth enough is a very strong assumption in some sense, because no, because so we have to solve this. Yes. So this problem here. It introduces the boundary, right? And so this is the boundary I'm talking about, which has to be smooth, is the boundary introduced by this variational problem. Okay.
And it seems it's not such a big assumption, but still it's difficult to prove.
Okay. Thank you.
Other questions or comments?
I was just wondering if there is any experimental motivation to choose this monokinetic initial data.
Well, so in the experiments, this is a very strong effect, so we have to deal with the Fokker-Planck operator. And in some cases, you can say that this is indeed rather small. So you imagine that, and actually that's what happened in the simulations I was showing you, that if the temperature is small, then it goes not too far from monokinetic case. So really, yeah, so that's the... So, and actually, in this case, even if you start not so small, then you will become small. Because of this, this tends to get you close to a monokinetic initial. This was the motivation.
Other questions? I will have just one. Have you considered the way the particle system converges to your equation? Some type of propagation of chaos or something, because you start from particles.
Yeah, no, as you probably know, when you have some Poisson equation here, then you're in trouble to show really that it does work. Well, let's say if you smooth out a little bit your interaction, then I'm confident there is no problem. But no. Should ask the question to Maxime. He probably has a lot to say on it.
Okay, so let's thank the speaker again.